You know Yellowstone, right? Geysers, amazing hot springs. It's all happening right there on the surface.
Yeah, spectacular stuff.
But your sources this week pointed us somewhere else entirely, way deeper. Something that might, change how we view the whole park.
Definitely. We're talking about the engine underneath it all.
Forget the postcards for a minute. We're diving into that massive magma system miles down.
And the timing's perfect.
Yeah.
There's this brand new study just published in Nature. It's giving us this incredible new look.
Ah, okay. So this isn't just like a small update then.
No, not at all. Researchers from Rice, University of New Mexico, Utah, UT Dallas, they've really pinned down something important.
Right. So for this deep dive, we're not just going over old territory. We're focusing on finding this magma layer they identified.
What it is, where it is.
Exactly. And what it means for, eruption potential. Plus the how, the clever ways they're seeing underground now. You wanted to get what this research really means for Yellowstone and maybe even wider. Okay, let's crack it open.
Well, the big question, the one that's kind of hung over Yellowstone geology for ages, is about that main magma reservoir. How deep is it really?
Yeah, I remember seeing numbers like anywhere from 3 to 8 kilometers. That's a huge range.
It is. Makes it really hard to model, to understand the dynamics. It's a lot of uncertainty.
Like trying to find something in a massive, dark basement, maybe. But this new work gives a more precise answer.
That's the headline, really. They've found a very distinct layer. It's magma, but it's rich in volatiles, gases, and water. And it's sitting much shallower, just 3.8 kilometers down.
3.8 kilometers, okay. And they're calling it a cap.
Yeah, think of it like a cap or maybe a lid sitting on top of the potentially much larger, deeper magma system.
A magma cap, right. So what does this cap do then? Is it dangerous?
Well, its main job seems to be trapping heat and pressure building up from below. It sort of acts as a boundary layer.
Okay, trapping pressure. So how on earth do you find something like that? Miles underground. You can't just, drill down there, can you?
Huh? No, definitely not feasible in Yellowstone. They use something called controlled source seismic imaging. Very sophisticated stuff.
Seismic imaging. Okay, that rings a bell. Using sound waves or vibrations to map things out underground, like for oil exploration.
Exactly like that, but maybe on a different scale here. They brought in this enormous truck, a 53,000-pound vibrosis truck.
53,000 pounds.
Yeah. This thing vibrates the ground in a very controlled way, sends seismic waves down into the earth, like creating tiny, focused earthquakes, basically.
Oh, wow. A man-made mini-quake truck, and then you listen for the echoes.
Pretty much.
Yeah.
As those waves travel down, they hit different rock layers, different materials. When they hit something different, like the boundary of this magma layer, some energy bounces back up, reflects.
And that reflection tells you what's there.
Tells you something is there. And by analyzing how the waves change their speed, their strength when they come back, you can figure out the properties of what they bounced off.
Okay, but you need to listen really carefully then.
Oh, yeah. They didn't just have one listening post. They deployed over 600 seismometers.
600?
Spread out across the northeastern part of the caldera. A huge network. They work closely with Jamie Farrell from the University of Utah on this interbeater. His team knows Yellowstone seismicity inside out.
Okay, 600 seismometers listening to waves from a giant vibrating truck. That must be an unbelievable amount of data.
Mind-boggling. And that's where the heavy-duty computing comes in. The lead author, Cheng-Wang Duan, he developed this really smart wave equation imaging technique.
Because the raw data wasn't clear, I'm guessing?
Not at all. He apparently said that at first, looking at the raw signals, it was almost impossible to see anything coherent, just noise. Yellowstone's geology is, messy, all that hot water and fractured rock.
Right, it's not like nice, neat layers everywhere. So how did they cut through that noise?
Duan's team used a clever trick in their processing, something called the Stolta function, short-term average over long-term average.
Stolta.
Yeah.
Okay, what does that do?
It's kind of like noise cancellation almost. It helps the algorithm distinguish the real, short seismic reflections, the signal from the constant background chatter, the noise. Duan mentioned it took a lot of persistence. They just kept refining it until the image popped out.
Wow. Persistence definitely paid off. So they found the boundary, 3.8 kilometers down. Did the models tell them what the cap itself is like? What's it made of?
Yeah, the modeling suggests it's not pure molten rock. It's more like existing porous rock, where the pore spaces are filled with a mix of silicate melt, the actual magma part, and these bubbles of supercritical water.
Supercritical water sounds intense.
It is. It's water under such high temperature and pressure that it's not really liquid or gas, but something in between. very good at dissolving things. Here, it likely comes out of the deeper magma as it rises and pressure drops a bit.
Okay, so it's like hot, bubbly, partially molten rock acting as a lid.
That's a good way to put it. They estimated the porosity, the empty space, is about 14%, and roughly half of that space is filled with these fluid bubbles.
Right. But okay, a hot, bubbly layer trapping pressure. That still sounds like it could go boom eventually, doesn't it?
You'd think so. But here's the really fascinating part. Maybe the most counterintuitive finding.
Uh-huh.
The study suggests this layer, because it's bubbly and maybe sitting in fractured rock, might actually be reducing the immediate risk of a huge eruption.
Reducing the risk? How?
They think the system is actually quite good at venting those volatile gases. The bubbles find pathways, little cracks and channels, and make their way up towards the surface.
Ah, like a pressure cooker letting off steam slowly through the valve.
Exactly. That's a perfect analogy. Brendan Schmidt, one of the researchers, he described it as the system doing this steady breathing.
Steady breathing, I like that.
The gases escape gradually instead of building up to an explosive point. And those geysers and hot springs we see, they're basically the surface evidence of this gas release. It makes a big sudden explosion less likely, at least for now.
So Old Faithful is actually a sign that things are stable-ish? That's wild.
It's a different way of looking at it, isn't it? But finding this out wasn't easy. They faced some real challenges doing the field work.
Yeah. Beyond just the noisy data and, working above a supervolcano.
Well, for one, they did a lot of this work right during the COVID-19 pandemic.
Well, yeah.
The logistics.
Oh, wow, yeah. Travel, safety protocols.
Exactly. And then there are the park rules. Yellowstone is a protected area. They could only operate that huge fibro-sized truck at night, and only from designated roadside spots.
At night, in Yellowstone, with a 53,000-pound vibrating truck.
Yep. Plus, deploying and retrieving over 600 seismometers across that terrain. It was a major effort.
That's some serious dedication.
It really is. And the payoff isn't just understanding Yellowstone better. This research is a big step forward for subsurface imaging in general.
How so? What else could this tech be used for?
Well, the techniques they refined could be applied to monitor other volcanoes worldwide. Maybe get better warnings before an eruption.
Okay, that's huge.
But it's broader than that. Think about carbon capture, finding safe places underground to store CO2.
Ah, right. Need to know the geology is suitable.
Or geothermal energy, mapping out where the heat is and how to access it safely. Even understanding earthquake faults better. Schmann pointed out how crucial imaging the subsurface is for all these things.
So it's not just academic curiosity about volcanoes. This has real practical spin-offs.
Precisely. It shows that with these kinds of innovative methods and that scientific grit we talked about, we can really start to see into these incredibly complex systems hidden beneath us.
Okay, so let's try and boil this down for everyone listening. Key takeaways from this deep dive. First, there's this distinct magma layer, kind of bubbly, found just 3.8 kilometers under Yellowstone.
Right, the magma cap.
Second, counterintuitively, this layer seems to be venting gas steadily, like breathing, which might actually lower the immediate risk of a massive eruption.
Yeah, acting like a natural pressure release.
And third, the way they found this, the advanced seismic imaging, is a big leap forward. It helps us see underground much better, not just at Yellowstone, but potentially anywhere.
Absolutely. Better tools for understanding volcanoes, resources, hazards, all sorts of things.
It's amazing, really, thinking about the power down there and how science is finding ways to map it out.
It truly is.
So thinking about these big advances in seeing underground, it makes you wonder, doesn't it? What other geological mysteries or maybe resource challenges do you think we could tackle with approaches like this? Where else do we need this kind of clear underground vision?
That's a great question. There's still so much we don't know about what's beneath our feet and how it connects to everything on the surface.
Definitely something to chew on.
Yeah.
How we balance understanding these natural forces with, managing our planet.